So this is the first part of tutorial 12, and as I said, it's gonna be like maybe 3 or 4 parts to this tutorial because it's really packed with all sorts of valuable material. So today we are going in this tutorial is supposed to be relatively short, not 1 hour and a half like the usual length. So today we are going to discuss types of singularities of functions, types of singularities, sorry for my handwriting. And the next topic will be calculation of residues of functions in these singularity points. And this is actually topic of questions 1 and 2 from your tutorial sheet 12. So bear in mind that this is a topic of these 2 questions. So, but first of all, we need some introduction. It turns out that I'm not quite finished with the previous tutorial, which was about expansion of various functions into a Lorentz series. Because some students asked me, what are the tricks you need to know to be able to successfully expand functions into a Lorentz series, as well as Taylor series, by the way. Are there any tricks or are there any operations which are allowed and which are not allowed? So let's discuss it first. So let's call it introduction first. So we need to finish with this topic. So unfortunately, in my previous tutorial, I was too concentrated on one of the canonical expansions, namely it was number 2, number 1 all the time. And we almost never had the chance to apply some others like sinus, cosinus or something, just to get the general idea what is allowed and what is not. So let's consider some example. Let's call it example 1 for today. So for example, you are asked to expand this function f of z, which is equal to sinus of 2z, for example, and in powers of z, as usual, in powers of z, because you know that if there are some other powers, you can always create a new variable t and reduce this task to the powers of t in this case. So we are not even going to discuss at the moment. So what will your course of action be? You know what? You need to look at the list of canonical expansions. I'm not going to show you this list because I'm afraid that I already threw it away from the last tutorial, but I still remember it. So of course you immediately realize that your function is most similar to this canonical function sinus z, which goes like z minus z cubed divided by 3 plus z to the power of 5 divided by 5 and so on. It has only odd powers 1, 3, 5 and so on. So our function, as I said before, is pretty similar to this function. And we are tempted to use this canonical expansion by substituting 2z wherever we see z. And the question arises, is it allowed or not? We still don't know. That's what we want to explore now. Let's pretend, no, it's me who is going to pretend that I don't know this rule. I'm just going to explore. Let's do this. So we take this expression, and wherever I see z, here, here, and here, I'm substituting 2z. 2z minus 2z cubed divided by 3 factorial plus 2z to the power of 5 divided by 5 factorial and so on. Of course, it needs some simplification. We can use the famous properties of the powers, so we can separate z from 2. It will look better. 2 times z minus 2 cubed times z cubed divided by 3 factorial plus 2 to the power of 5 z to the power of 5 divided by 5 factorial. That's it. So the question is, was it allowed to do, and is our answer valid? And you know what? You need to recall the goal. What is the goal of our, what was this assignment of our problem? We needed to present the answer in a form of a series in powers of z. Can you see powers of z here? Of course, look at this. This is z to the power of 1. This is z to the power of 3, z to the power of 5. And the remaining expressions, they're not even expressions, they're just numbers, numerical coefficients. So we did achieve our goal. That means that we didn't violate, the assignment of our problem. We obtained exactly what we asked to. So the conclusion is that it is allowed operation. Let me write it down. So instead of z, you allowed to substitute something like k times z. Instead of z, you're allowed to substitute some constant times z. For example, 2z, like we just did now, 3z, maybe z divided by 2. It's again, it's another constant, but fractional constant. So it's a good news that we managed to figure out that this is one of the allowed operations. Let's consider one more example. Example 2, for example. So f of z is e to the power of z squared. And the summit is the same. We need to expand it in powers of z. And of course, you immediately remembered, or maybe you have your cheat sheet at your hand, that there is a canonical expression which looks quite similar to this function for exponent. So it looks like this: 1 plus z squared divided by 2 factorial plus z cubed divided by 3 factorial, and so on and so on. So this is a canonical expression without any limitations. The region of convergence is the whole plane. Any z will do to satisfy this formula. So, and now we have another idea. We start thinking to ourselves, what if we just substitute z with z to the power of z squared? Is it allowed to do so or not? Let's explore this topic. Let's just do it, and then we can discuss it. Okay, so wherever I see z, I'm substituting z squared squared again, divided by 2 factorial plus z squared cubed divided by 3 factorial, and so on and so on. Let's just simplify this a little bit. So this will be z to the power of 4, of course, divided by 2 factorial. And this guy will be z to the power of 6, and so on until infinity. So, and the question the same is the same as in the previous example. Have we managed to achieve our goal? Did we obtain the expansion in terms of z? Yeah, of course. Look at this. Z is only present in the form of this function, z to the power of 2. So it is expansion in terms in powers of z. So our conclusion again is the same. So it turns out that instead of z, we can substitute z to some power k. And even if this power is negative, look at this. You can substitute 1 divided by z to the power k, because it's not Taylor's expansion anymore. It's Laurent's expansion. And in Laurent expansion, you can easily have these negative values, negative powers, sorry. So let's consider, this sounds so unusual that we need one more example. Let's make a very small example, something like, what else? Wait, we haven't considered cosine. Cosine of 1 divided by z. Let's consider this function. And the assignment is the same for all my problems today. So, of course, we can consider this canonical expansion of cosine, which looks like z squared plus z to the power of 4 divided by 4 factorial, and so on. So it has only even powers, as you can see, and no limitations when it comes to region of convergence. Okay, in this case, you compare your given function, your concrete function, with this canonical one, and you attempted to substitute 1 over z instead of z everywhere. And this is quite unusual, because you had never come across anything like this before you started studying complex variable theory. That is why we should be cautious. Who knows? Maybe this time it will be failure. So as you can see, I'm substituting 1 over z instead of z everywhere. And I'm trying to do it very cautiously. I'm not writing, I'm writing in too much detail probably, but that's for good reason. Okay, now let's simplify this, because it looks ugly. So we can rewrite it as 1 divided by 2 factorial times z squared in the denominator. Looks much nicer. Plus 1 divided by 4 factorial z to the power of 4 minus 1 divided by 6 factorial z to the power 6, and so on. So we did get our Laurent's expansion. By the way, it contains mostly negative powers, with the exception of the first term, of course. But can it be called expansion in terms of z? Look at this. You already, just like in the two previous cases, you have only power z. It means that it is called expansion in powers of z. Even though these powers are negative, but you know it's quite acceptable in terms of Laurent's series. It's not Taylor's series anymore. So this is our next conclusion. So as I said, I already wrote down this conclusion. Even if you need to substitute z with something like 1 over z in some power, it's still allowed. It still doesn't break your result. Your result will be the same. Okay, so far everything was so nice, and the question might arise, but are there any exceptions? Are there situations when it's not allowed, when you find the failure? And let's consider the situation. So f of z is equal to e to the power of z plus 3. Very interesting, not very interesting function, just very popular function. Let me copy this canonical expansion again. Oh, sorry. The letter should be z, not x anymore. So I'm copying this canonical expansion for you. And now the question arises that, so we are so familiar, we have so much experience now. What if we just substitute z with z plus 3? Quite a nice idea. Look at this. Let's do it. Z plus 3. So I'm plugging in z plus 3 even in parentheses everywhere instead of z. And some people might think, this result looks quite nice. It looks like a very beautiful, quite decent Laurent's expansion. But did we achieve our goal? Look at this. Look at how z appears. Z appears always like z plus 3, z plus 3 in some power. What does it mean? We did achieve expansion, but it's not quite what we asked to achieve, to obtain. We were asked to obtain the expansion in terms of z, but this is in terms of z plus 3, in terms of z plus 3. So we got wrong answer. We didn't obtain what we were asked to. That is why it's not allowed. So it turns out that our conclusion that it's not allowed to substitute z with some z plus constant. Because even though you still get quite a decent expansion, but it's not what you need to. You need to get expansion in terms of z, not plus z plus 3 or something else. So this is why this is a failure. Where's the correct solution? Let's write down correct solution. Correct solution. This was incorrect. This was our first attempt and we failed. We realized that we failed. Correct solution means that you need to prepare your function first. You need to process it somehow to prepare it for using this canonical expression. But there's nothing easier than this. You can use these very well-known properties of powers. You can write it as like e to the power of z times e to the power of 3. And e to the power of 3 is better to put it in front as a coefficient, numeric coefficient. And instead of e to the power of that, you can substitute, I'm writing in green for some reason, I don't know why. You can just substitute this canonical expression. Plus z squared plus 2 factorial plus z cubed divided by 3 factorial z. And of course, it's better to make this multiplication. E cubed plus e cubed times z plus e cubed times z squared divided by 2 factorial, and finally e cubed again, z cubed divided by 3 factorial, and plus so on. Look at this. This expansion, this is another expansion, Lorentz expansion, but this time it's a correct expansion. No, why? Because we can see only powers of z here, not powers of z plus 3 or something like in the previous case, but that plus 3. So this is the right solution. So it turns out that the only operation which is not allowed to apply here is to do this thing, because you will end up having some other powers instead of z. So that's it. This was the introduction. This was the review, maybe supplement material to the previous tutorials, because even though my previous tutorial was quite long, almost 1 hour and a half, but it happened so that I used only one of these canonical expansions all the time. And that is why you might have got a wrong impression that, you are going to deal with this expansion only all the time. Okay, so this was introduction, as I said before, and now it's time to plunge into our new topic. So our new topic, as I said, will be points of singularity. You already know what they mean, but this time we will need to determine their types. It turns out that there are three types of singularity points, And today we are going to start discussion as to how to determine their types. Also, we are going to start talking about residues of the function, given function in its singularity points. These things can be done together, along with each other. Okay, so let's start with singularity points. Let's write the singularity points. What are these guys? Let's refresh our memory. So, for example, if you consider f of z is equal to sinus z divided by z, what is singularity point? A singularity point is the point where your function doesn't make sense, when the domain of the function just breaks. Of course, this is the point z is equal to 0. I put z0 here, substitute, just to have a neat writing. Another example. So, for example, you have this fraction 1 plus z divided by z minus 3, where this function doesn't make sense. At the point z is equal to 3. So this is your singularity point. So that's how to determine singularity point, nothing fancy. But now, how to determine their type. How to determine the type of singularity point or just singularity, and how to calculate residue. Calculate residue of your function. Look at this notation at the point 0. So how can we do it? It turns out that there are two methods. I'm afraid of running out of space on this page. But maybe I'll manage to squeeze it in. So there are two methods. Let's write it down. This very important idea. There are two methods which allow you to do this. So the first method and the second, there are even three methods, but this is not. So the first method uses expansion to Laurent series. So method one says that f of z should be expanded into Laurent series, and we are going to discuss it next. So you just need to know that this is the first method. And there are two other methods which are considered to be shortcuts, but in reality they are not quite short, ironically. But still we need to call them shortcuts. So this will be method 2, and even method 3. So as you can see, I'm going to explain you even 3 methods. But you know what? As for methods 2 and 3, they will be recorded in the next tutorial. In this particular tutorial, in the current tutorial, I decided to focus only on the first method, which uses this Laurent's expansion to Laurent's series. So this will come in the next video. Okay, so let's plunge into method 1. So let's give it a name, method 1. How exactly you should act. Let's write down this method a little bit. So let z0 is a singularity point of function f of z. What should you do? How exactly this expansion should be? Let's write it down again, this algorithm, this idea. We need Laurent's expansion. Of our function z, of f of z, in powers of z minus z0. Look at this. So if you had singularity z0, that you need expansion in terms of z0. So which looks, let me remind you how this Laurent series looks like. So f of z, I already wrote it to you in our face-to-face tutorial, but nevertheless. So this is so-called regular part, which contains non-negative powers of your z minus z0 plus so on. But you can also have so-called principal part. Let's write it down. So c minus 1 divided by z minus 0 plus c minus 2 z minus 0 squared plus z minus 3 z minus 0 cubed, and that's enough, plus so on. So you will get something like this. What next? What next? And now you need to pay all your attention to principal part. This is called principal part, as I told you before. Principal part. And I highlighted this idea to you many times that it's going to be super important. And now this moment has come when the principal part will be super important. It turns out that to determine the type of singularity point, you need to look at this principal part and realize how many terms are there in your principal part. So let's denote it like capital eta N. So N is the number of terms number of terms in principal part. This what is going to be crucial. Okay, now I need to turn the page because I want to draw you a little table. So it turns out that there are three types of our singularities. Let's divide our page into three columns as usual, and it all depends on what is the result related to n. N could be equal to 0. N could be just some finite number, and n also can be infinite number. So 0, finite, and infinite. And so what does it mean if n is equal to 0? It means that no principal part at all in your expansion. No principal part. Okay, no principal part. And this case, Z0 is called removable singularity. Removable singularity. So this is the name of the first type. Removable singularity. Sorry. So what about this? Let's move to the second column. In this case, Z0 is called pole, like a north pole, like a south pole. Pole of order M, and of order M, and I need to explain what is this order. Let's just write it down. Where this M is the highest negative power, So in case of pole, the number of terms in this principal part is limited. It's just finite number, like 3, 5, maybe 10. It doesn't matter. Just limited, not infinite number. And the highest negative power shows you the order of this pole. So this is the second name, pole of order M. And finally, you have the last case when you have infinite number of terms in your principal part. So in this case, this singularity point is called essential singularity. Essential singularity. Okay, so this is the classification of these three types of singularities. And for the next half an hour, it's going to be our main task as to how to determine this type. And what about residues? I started talking about residues, but so far I didn't give you any formula or something. You know what? It turns out that if you manage to expand your function tolerance series, there's nothing easier than to calculate residues. Residues is the same for all the three types of singularities. This is the notation for residues. It turns out that this is just a coefficient in front of 1 divided by z minus z0. This is a coefficient in front of power which is equal to -1. So this is formula is correct for any type of your singularity. That's it. So this is a theoretical basis for our today's tutorial. And now it's time for us to start solving problems. So all problems, and I'm going to give you like 3 or 4 problems. They all will have the same assignment. So the assignment will be find all singularity points of function f of z, determine their types, their types, and calculate residues, of your function in this singularity points. So this will be the same, absolutely the same assignment for each of these 3 or 4 examples which I prepared for you. Okay, it's time for start. So our first, I'm going to enumerate them again. So the first example is actually question 1a from your tutorial sheet. I decided to spend it to waste it. So in this assignment, you are given a function f of z, which is hyperbolic sinus of z divided by z. And so we need to do these three assignments. The first assignment is to finding singularity point. The second is to determine their point. And the third assignment, calculate residues. So let's start doing it. So it's pretty obvious that singularity point is that 0 is equal to 0, just 0, because division by 0 is not allowed in any field of mathematics, including even such a weird field as complex number theory. Okay, it means that we need to expand our functions in powers of z. But you know, it's very convenient. We already recognize this function. It's in our list of canonical expansions. So all we need to do, we need to substitute this expansion here, this formula, instead of denominator, and see what happens next. So this canonical expansion looks like z plus z cubed divided by 3 factorial plus z to the power of 5 divided by 5 factorial and plus so on. I think it's enough. And I'm copying the denominator. Of course, we need to simplify this expression, and it's very easy. You need just to divide every term by z. So let's do it. It will be 1 plus z squared divided by 3 factorial. Here we have z to the power of 4 by 5 factorial, and so on. You can easily imagine that the powers will be increasing all the time. This is the second power, fourth power, 6, 8, and so on and so on. Okay, so this is our result. This is our expansion in powers of z. So, and now we need to take a closer look and look at what? We need to have a look at the principal part. But you know what? What a disappointment. No principal part at all, you know, this time. No negative powers. No principal part at all. No principal part. It means that our n is equal to 0. I prefer to use this notation because it's very convenient. Okay, so what does it mean? What does it mean? Let's have a look at our table, our classification table. So it turns out that we are inside the first column now. And in this case, this singularity point called removable point. So our z0 is equal to 0 is removable singularity. Okay, removable. Very bad handwriting, of course. Okay, so we obtained our first result. What about residues? What about residue? So residue of our function f z in point 0, what it will be? According to definition, it's a coefficient in front of 1 divided by z. But you know what? 1 divided by z, this term is simply missing in this expansion. It means that you can imagine that it's still there, but this coefficient 0. So our residue is equal to 0. So it looks like we succeeded with our very first example. It wasn't very difficult. It was just a good warm-up. Okay, let's move to the second example, which I prepared for you. Second example is actually about, from your tutorial sheet again. This is question 1b. And you are given function like f of z divided by z plus 1 divided by z squared. This is a fraction again, and fractions can be really difficult, to be honest, as you probably noticed in the previous tutorial. But you know what? We are very lucky. This is a super simple fraction. What can you do to this? You can just divide, just like we did before. You can divide every term in the denominator by z squared. What will you get? You will get 1 divided by z plus 1 divided by z squared. And you know what? This is super funny example, actually. It's already the answer, right? It's already the answer. We even forgot to discuss singularity point, sorry. We should have started with singularity point. So singularity point is 0, of course, just like in the previous example. But you know, and we obtained this expansion in terms of z surprisingly easy. Look at this. We didn't even have to draw circles or something like this. It's happened just naturally. And you know what? This is actually principal part, because this expansion is very strange. It contains only two terms, but nevertheless, these terms have only negative powers. So this is principal part. Very funny example. Principal part. Principal part. What about n? What is the number of terms in principal part? Of course, 2. And what does it mean? It means that if we look at our table, we realize that we are here in the second column now, because finite, n is equal to 2, it means finite. So it means that this is pole. Aha, very interesting. So our singularity point is pole, but when you come across a pole, it's absolutely necessary to determine its order of the pole. What is the order? The highest negative power. What is the highest negative power here? 2, of course, 2. So this is a pole of order 2. I prefer to write this m is equal to 2 instead of words, pole of order 2. But if you prefer, you can always give the answer in this form, pole of the order 2. So let's see, look at this, how easy it was. What about residue now? So residue of our function f of z at point 0, what can it be? Again, according to definition, this is a coefficient in front of 1 divided by z. And this time we do have term, which looks like 1 divided by z. What is the coefficient here in front? 1, of course. So our answer, residue, is equal to 1. So we managed to solve 2 problems. Another problem will be, quite easy problem. Let's move to the third problem. Third problem is question 1D from our tutorial sheet. So this time we are given f of z is equal to e to the power of 1 divided by z. What is the singularity point? Pretty obvious. It's z0 is equal to 0, of course. We have the third example with the same singularity point. Okay, it means that we need to derive expansions in powers of z. How can it be done? Do you remember our introduction? So I think that I already discussed this function. It looks pretty similar to exponent e to the z, with the difference that instead of z, you should substitute 1 over z everywhere. So let's do it. I'm not going to write you this canonical expression. You can have a look at it. So 1 plus 1 divided by z plus 1 divided by z squared divided by 2 factorial plus 1 divided by z cubed by 3 factorial plus so on. I'm running out of space, unfortunately. So let me just simplify this. 1 plus 1 divided by z is the first term. The second will be 1 divided by 2 factorial z squared plus 1 divided by 3 factorial z cubed, and so on, and so on, and so on. Okay, so this is expansion in terms of z. No one has doubts about it. But now we need to have a look. Now we need to find the principal part. Where this principal? It's here, principal part. 1 is not considered to be principal part because 1 corresponds to z, to the power of z to the power of 0. It's not negative power, only these negative powers. So this is our principal part. Okay. How many terms can you see in this principal part? Infinite number of terms this time. Infinite number of terms. So it means that now we come across the third column, the third case represented in the third column. So in this case, our z is equal to 0 is called essential singularity, essential singularity. Okay, so what about residue? Residue of our function at the point 0 is coefficient in front of this term. Look at this term, 1 divided by z. Again, like in the previous case, it's equal to 1. So as you can see, all the 3 examples were pretty easy. But now I have one more in store for you, which is going to be a little bit more interesting. A little more interesting, but where is it? I prepared it somewhere. So example number 4 is going to be much more serious. So be prepared. Okay, sliding out of view. So here's my example number 4. It's not from tutorial sheet. Maybe it's from study guide. Maybe it's from of my own invention. To be honest, I don't remember where I got this example. Doesn't matter. Okay, so what can we see here? Quite bad news. We have even 2 singularities here. It means that we have to do 2 expansions. So it's twice as long as usual, this problem. Okay, let's start. Let's start with the first singularity, z1 is equal to 0. And the second singularity will be minus 1, of course. Okay, let's start with that 1 is equal to 0. So we need, it means that we need to get expansion in terms of z. But you know why? This function is a little bit tricky, is a little bit difficult. It looks annoying because you already watched my previous tutorial 11 and you noticed that it's not very nice to deal with this, to deal with fractions. You know what? In my introduction, I actually forgot to tell you about one more trick which can be used for Taylor's expansion. So let's just forget about this task for a while. We need to be prepared. You know what? I gave you many tricks which mathematicians use to be able to make these expansions faster. Let's just refresh them. So instead of z, you can substitute k times z, where k is constant. Another allowed operation, instead of z, you can substitute z to the power of k, or even z to the negative power, 1 divided by z to the k, and so on. This was the set of allowed operations which allow you to write these expansions quite efficiently. But you know what? I forgot to mention one more very beautiful one. It turns out that you can actually differentiate or even integrate, this series, Laurent series, as well as Taylor series. Let's discuss it. You know what? Let's consider, for example, this canonical expansion. 1 divided by 1 plus z is a very well-known expansion. 1 minus z plus z squared minus z cubed plus z to the power 4, and so on. The only limitation, the only frustrating thing about this expansion is that it has limitation, it has region of convergence, which should be observed. Okay, so let's use this as an example, and now I'm going to give you very interesting examples. So f of z is given almost the same expression, but a little bit different. And the assignment will be to expand this function in powers of z. So I forgot about all these residues, types of singularities for a while. I'm getting back to these techniques which mathematicians use for expanding functions. So look at this function. Of course, we attempted to use this one, but then we realized there's no way of using. We can't just, substitute the whole series instead of 1 divided 1 plus z. And because there's no way of squaring the whole series. You can't square infinite number of the sum of infinite number of terms. So it looks like it's a complete dead end. But you know what? It's not. It turns out that we have this beautiful, very beautiful idea. It turns out that this function is almost derivative of this canonical function. Why I'm saying almost? Because you need to put minus sign in front. And in this case, it will be absolutely true. So this is absolutely beautiful idea. And what can you do? You can substitute this expression, this function in the parentheses with this canonical expression, and then you can just derivative. And of course, you need to write this minus. So it's absolutely beautiful idea, and I think you are going to appreciate it. So let's do this. So I'm going to substitute this expansion instead of this function, canonical function, plus minus so on. And I'll have to, the only thing which I need to do, I'll have to take derivative, but this is super easy to take these derivatives. Okay, let me put another page here. It's not horizontal. Okay, so I'm rewriting, look at this, I'm rewriting this minus in front. And of course, so derivative of the first term is just 0. Minus 1 will be derivative of minus z. Here we'll have 2z. Here we have minus 3z squared plus 4z cubed and minus so on. And now we need to multiply it by 1, of course. 1 minus 2z plus 3z squared minus 4z cubed and so on. And so now you're pretty familiar, and now you familiarize yourself with this very beautiful trick, which can be used to be able to apply canonical expansions to your concrete function. So what was the main idea? Let's revise it again. I noticed that my function is just a derivative of this very well-known canonical function. That's it. Sometimes you could notice that your function is, on the contrary, the integral antiderivative of some canonical function, and so on. You can play around with this guy. And by the way, this operation of differentiations doesn't break your region of convergence. It will remain the same. There is a special theorem devoted to this fact. So now we are ready. We got this, abstraction a little bit, but now we are ready to understand problem 4. Let's get back to problem 4. So again, we are given this function f of z, which looks like this quite annoying fraction, z plus 1 squared. And we were asked, as usual, we were asked to determine all the singularity points, to determine their type, and calculate residues at this point. And so now we can start, because we are already armed with a very nice trick. Okay, as we discussed before, as we noted before, we have the first point of singularity is 0, and -1 will come next. Okay, so z1 is equal to 0. It means that we need to expand this function in terms of z. I think that we can rewrite our function as 1 over z, like a coefficient in front, and this will be our main function here. You're pretty familiar with this trick. So 1 over z can be treated as just like a fraction. What about this guy? You know what? We just discussed this guy. Look at this. This was our previous example, this green one. We just managed to expand this function into a Lorentz series. So we can use this result immediately. So this function, but I lost it already. It's here. So almost threw away this variable page. So let's substitute the result from the previous previous example, sorry. Plus 3z squared minus 4z cubed plus so on. And now we need to perform this multiplication, of course. 1 divided by z minus 2 plus 3z minus 4z squared and plus so on. I think it's pretty enough. Okay, now we need to find our principal part. You know what? It's very funny, but it consists of one term only, this principal part. But nevertheless, such thing happens. What does it mean? It means that number of terms in our principal part is 1, and this is our favorite case 2. Our favorite case 2. Look at again this table. Yeah, here is this table. So this is a case corresponding to the middle table. It corresponds to finite number of terms, which is pole. So it means that our z1 is equal to 0 is pole of which order? What do you think? The order is the highest negative power, but we have only one power, so it plays the role of highest. So it's I think that there is a special term for this situation, like simple pole or something. I'm not sure. I prefer to say pole of order 1. Okay, our next step is to find a residue of our function in this point, which is 0. What is residue? As usual, this is coefficient in front of 1 of z, but this coefficient is 1. Somehow we keep getting 1 all the time, but the idea is just happened coincidentally. Okay, so we did explore the first point of singularity, which was z1 is equal to 0. Now it's moved to time to move to the second point of singularity. So the second point will be z2 is equal to -1. And I think it's better to copy my function here to this page, otherwise it will be very difficult. Z plus 1 squared. So what do we need in this case? So finally, our singularity point is not 0 anymore, finally. It means that we need to make expansion in powers of what? Powers of z plus 1, because z minus this guy, z plus 1. How can it be done? You know the trick from our previous tutorial. The best way is to denote it like new variable t, and rewrite the whole function in terms of t as well. It will be much nicer. So let's do it. But we need to prepare z first. So instead of z, we are going to substitute z is equal to t minus 1. Okay, let's start. So here we have z, and I'm substituting t minus 1 instead of it. Here z plus 1, but z plus 1 is equal to t. So it will be divided by t squared. And for this function, this camera is not quite blurry, it's a little bit blurry. And in this case, instead of exploring, the point -1, it will be exploring the corresponding point t is equal to 0. which means that we need expansion of this function in terms of t, in terms of powers of t. So we reduced our task to the more familiar task. But I think we need to rewrite the function. You know what? 1 divided by t squared should be written in front, and this function here. And again, it almost looks like a canonical function, but with the difference that it should be 1 minus t. So it could be resolved very easily if you put minus sign in front, if you pull it out. And in this case, this fraction is just canonical expression from our list of expansions. So let's substitute it here. 1 plus t squared plus t cubed plus so on. Now we do this multiplication. Minus 1 divided by t squared, minus 1 divided by t, minus 1, minus t, and minus t squared, and so on and so on. So you realize that your principal part is here. It consists of two terms only. It means that this is a pole again. So our point t is equal to 0, which is actually z is equal to z2 is equal to minus 1. It's pole again. Which order? What is the order of the pole? The order of the pole is 2, because this is the highest negative power. Okay, what about residue? Residue f of z at the point minus 1 is c minus 1. Again, what is c minus 1? This time it's minus 1, just for a change. So this time our residue is minus 1, because we have this point, this coefficient minus 1. So it looks like that's it. That's all I wanted to... no, that's not it. I wanted to discuss you when this... It looks like this is a super convenient method. When you manage to expand your function into Laurent series, you're sort of killing two birds with one stone. You can immediately determine the type of your singularity, and at the same time, you can calculate your residue like a piece of cake. So it means it looks like this is a perfect method, and I completely agree with this. This is a perfect method. This is my favorite method. Every time I need to find the residue of the function, I always look for expansion into Laurent series. But are there cases, are there situations when it's not convenient or maybe even not possible to apply this method? Let's discuss it. It's super important because you need to know the difference. When it's not convenient, when is this method, which is method 1, do you remember? When is this method not convenient, or even impossible, I would say? Let's discuss. So my first example is something like this. For example, f of z is equal to something like z plus 1 cubed times z minus 3, and times maybe something else even, just to scare you off completely. Look at this. This is fraction, of course. And we do know how to deal with fractions. You can always expand it into the sum of partial fractions. There's nothing impossible, but you know it's like such a tiresome task. It's such time consuming. So in this case, it's still possible to do it, but you know what? You're completely put off by this situation. Don't do this. Wait for the better methods to come in the next tutorial. So this is just long. This is just not convenient. And there is another case where it's simply possible. So for example, look at this: z divided by sinus z. Of course, we do know the expansion of sinus z into the series, but can we substitute it here? Of course, we can try at least. Let's do it. But there's no way of simplifying this. You know, I'm afraid that you can't simplify this. You can't get the answer in the form of Laurent's expansion. So it's impossible to do it. So we definitely need some more methods, maybe some shortcuts, some ways around it, because unfortunately there's nothing perfect in life, and there's nothing perfect in mathematics. However appealing this method might look, but it has its flaws, as you can see. Sometimes it's just time-consuming to try and expand, some terrifying fractions into this canonical expression. And sometimes it doesn't seem impossible. Maybe there are some ways, but we are not going to discuss them. It seems to be too complicated. By the way, among your questions 1 and 2 from tutorials, there is only one, I suppose it's question 1c, which is impossible to be done in this way, applying this method. So bear it in mind. And of course, as usual, to give you a chance to polish up your skills, to try your hand at this topic. I'm giving you now the homework, little homework, consisting of seven. Oh, sorry, consisting of seven different assignments. So the assignment for the whole 7 problems is the same. Determine the types of singularities and calculate residues in these singularities. So as usual, try to stop this video, try to pause it before look at the answers. And now the answers are here. The answers here. To make your life a little bit easier, I even, I even wrote the number of terms in the principal part for you, even though usually you are not asked to do it, but I just did it for your convenience. So this is your answers. So okay, so the topic of our next short tutorial will be devoted to this remaining 2 methods. To remember, oh, there's my first page of this tutorial. So let's have a look at the first page of our tutorial. As I said, there are like 3 methods as to how to determine these types of singularities and how to calculate residues. We covered only this first method, the most beautiful one, the most universal one, but unfortunately it's not perfect. And so the next tutorial, which will be devoted to these remaining 2 methods. They don't look so appealing anymore, but in any case, they are much better than struggling with the Laurent series in some complicated cases. So that's it for today. That's it.